Okay, welcome. Welcome back from spring break. Hope you had an enjoyable break. So last time, so we've been talking about various aspects of security in typical security practices. Last time we dove into management of users and user authentication and access control and things like that. We're continuing this time with a focus more on the network level. How are the detail, a little bit more details about how corporate networks are typically organized and managed and the security issues surrounding them. So we'll look at first some general security practices, review some of the concepts we've been talking about, such as network compartmentalization and stuff, and get a little deeper into how some of those are commonly implemented. Look into things like VPNs and network perimeter security practices, and logging and backups. Okay. So we've seen a number of a lot of breach incidents already. In fact, I think we've even mentioned this one at least once, or the big Sony breach of a few years ago. This is a great example of a strong network level attack in which the attackers got into Sony's network, installed sophisticated backdoors and proxies to move laterally through the network and get a lot of different information across the network in different ways. And of course, they were apparently wanting to try to pressure Sony into not releasing this movie that was called The Interview, which of course did get released. So another classic instance of this kind of attack was the Target breach back in 2014, where it was discovered that a huge portion across Target's entire payment system, these credit card scanners across many thousands of Target locations were malware infected by malware that could basically send all the credit card numbers to the attackers and basically kind of steal all the 40 million credit card numbers. So these were very strong, but unfortunately all too common network level attacks that are of the type that are more readily feasible when network security isn't as tight as it could be. So let's look at some of the organizational practices. So we've already talked about some of these concepts at a high level. For example, the demilitarized zone, the DMZ. Segmenting networks so that to keep this small DMZ, which is only for the small set of services that have to be accessible from both within the network and from both the public network. But then we'll also get into other more low-level detailed concepts such as virtual LANs or VLANs for partitioning networks into smaller segments. And so, so in general, once again, network compartmentalization is the process of taking a big network and breaking it up into smaller subnetworks or zones or VLANs or different types of compartments. Basically for two reasons. First of all, to ensure that if any one compartment gets compromised in whatever way, try to make it harder for the attacker to use that compromise to go into other compartments and compromise more of the network. And then, of course, perimeter defense is trying to protect the the whole corporate network from the external attackers on the external internet. So. In many cases, so one classic scheme, way to view network security that is derived from the operating system architectures. It actually goes back before Unix. There was this old system called Multics. Anybody heard of Multics? Oh, good. Yeah, exactly. So what was Multics? Do you remember what was Multics and where? Yeah. Yeah, that's okay. So this was this great big operating system, mainframe operating system that was developed at MIT and cooperating companies. It was supposed to be, the big successor to. Well, it was in its day, kind of the big operating system project. Unix was Unix kind of came later. Dennis Ritchie, Kernighan and Ritchie, Bryan Kernighan and Unix was basically a joke. The name Unix was a play on Multics. They were decided, well, this Multics thing was, kind of everything. It had every possible feature. And they decided, let's simplify, let's create something smaller, simpler, and see if, what we can do with that. So they came up with Unix, which was basically a language joke based on Multics. And of course, Unix is what took off, and Multics has been mostly forgotten. But I'm glad it's not completely forgotten. But Multics had and came up with many ideas, including about security, that are still with us in various forms, including this ring architecture, which is also still exists in the form of the x86 processor. Right? How many of you have dealt with segments and privilege level, the 4 privilege levels in x86? Taken an x86 course? Good. So that's another holdover of the Multics ring architecture that's not used much anymore. Nobody really uses x86 rings other than 0 and 3, the two kind of extreme ones. But the notion of concentric rings, kind of an onion-like architecture with concentric rings, has still persisted in various ways, and it kind of persists in the network security environment, even if it's in a much more informal, ad hoc way. So in many cases, many network systems are built with kind of the crown jewels in the innermost ring, the most protected, most access restricted, and then in successive outer rings, you consider the successive outer rings slightly lower sensitivity level, and so on as you go out, and then the big bad, completely untrusted external world is outside of the outermost ring, and that is one sometimes reasonable way of looking at this compartmentalization. But many people have, I think, rightly realized that picture is often too limited, because within any given ring, you don't necessarily want everything in at that sensitivity level to have access to everything else at that sensitivity level. So you kind of want to divide up the rings to compartmentalize within the rings and not just between rings. And so in more sophisticated security architectures, including network compartmentalization architectures, it's often a practice to create to divide up networks into compartments or subnets or VLANs, various types of compartments for specific purposes, such as say user zone 1, production zone 1, corporate services zone, external zone, development zone, so to define purposes for different regions of the network, what kind of machines, laptops, desktop servers are supposed to live there, and which other zones are they supposed to be able to communicate with using what applications and port numbers, what policies should apply for communication between any zone and any other zone, right? And usually there's, big companies tend to have a backbone network where, kind of any communication with anything else ends up ultimately going over a common set of physical network infrastructure, sometimes over VLANs or WAN connections between different offices and locations. And so that's all part of the backbone communication infrastructure, but then the individual units kind of hang off of that. And then you use some kind of firewall functionality separating each zone from all the others to control what can access what else and maintain as much compartmentalization as possible. And so again, finer granularity compartmentalization is in principle good for security because it potentially, hopefully reduces the amount a given attacker can do if they break into any one zone. But on the other hand, it can backfire. It can also have disadvantages and even backfire if it's, for example, too complex. There's too many zones for the administrator to get right, and then they make mistakes and leave some wide open gaping holes that the attacker get in because of those mistakes. So that's, there's always that balance between trying to get the most fine-grained, tightest security versus managing the complexity. So, so I've talked about the DMZ before. Just a review, that's the part of the network typically that has to be accessible both to the external world and to the internal network. So I won't belabor that since we've already dealt with it, other than just to mention that kind of when we get into how to implement it, there's many different ways to implement all of these types of security architectures. In particular, even though kind of having a DMZ is pretty much standard, there's two fairly standard different ways to implement it. You can, for example, you can just implement it with one switch, one kind of front-end switch router firewall between the internet, the DMZ, and the corporate network, the rest of the corporate network. Or you can implement the DMZ as kind of something that's wedged between two separate firewalls, an internal firewall and an external firewall, like on the other picture. So, and you can, in principle, implement all the same rules, whether the same policies, either way. It's just how you set it up. But each one has potential advantages and disadvantages. Can you think of particular advantages? Why would you want one? Why might you want one of these implementation strategies versus the other? Any ideas? Yeah.
The first requires less machines.
Yep. Yeah. So you save hardware. Clearly, you need only one switch, one firewall rather than two. Good. How about why might you want to spend to pay the cost of having the second switch and go for the other approach? Hmm? Yeah. Anyone? Single point of failure. Yeah. So exactly. So if you're completely dependent on that one switch and something's wrong, the switch is either compromised, buggy, a rule is wrong or something, so the attacker gets all the way into the corporate network, whereas if you have those two switches and they have some diversity, diversity of maybe they're different types of firewalls from different manufacturers, maybe they're at least administered by different people, or have some diversity between them, then maybe you have more hope that an attacker that somehow gets through one won't be able to get through the other and won't be able to get all the way in, right? So that's a legitimate, potentially legitimate reason. On the other hand, there's often ways that, often those two firewalls are the same hardware, so, administered by the same people in more or less the same way. So it might not, it's basically debatable how much additional security you're necessarily getting in practice from the two switch arrangement. You might be getting some security, you might not. It depends on a lot. So, but anyway, that's just to point out, the many different options in implementing these policies. But now, so that's an illustration of some of the options. I want to dive now into the more low-level details of one of the most common ways of implementing either coarse or fine-grained compartmentalization in networks, which is using VLANs. So how many of you have configured VLANs or dealt with VLANs in some way? Okay, a few. Okay, good. So VLANs are a common, now pervasive feature of practically all Ethernet switches that basically they're a layer 2 Ethernet MAC level feature of most switches and routers that allow you to basically add tags and assign Ethernet packets to separate logical domains, so that users attached to a switch associated with one VLAN by default won't see traffic that gets sent to any other VLAN. So each VLAN basically will act at Ethernet level as its own separate broadcast domain, so packets from one VLAN won't automatically go to another VLAN at all. And instead, you typically use layer 3 IP routing with internal firewalling rules to determine when packets legitimately can and should cross VLAN boundaries. So you typically set up an IP level network with a separate IP subnet for each VLAN, and you rely on level 3 IP routing to bridge those VLANs when you want them to, but keep them separate logically in terms of the Ethernet level transmission. So this is a diagram of one of the, just kind of an example of the one way this can work. For example, you've got a bunch of switches, these VLAN-enabled switches, managing the backbone network there in the middle, and some edge switches managing the DMZ area to the left between the main corporate network and the internet, so for example, and then each of these VLAN, the switches in the center, where you see several lines going through the backbone switches in the center, those are tagged, what we call tagged VLAN links, where the switches know that they're talking to a neighboring switch, and they explicitly send prepend little VLAN tags, just numbers saying, this particular packet is on VLAN 102, whereas this other packet is on VLAN 101, and so on, so that any packet going across that backbone is explicitly labeled with which virtual network, which subnet, which compartment it's supposed to be on, right? And so those backbone switches are basically trusted, and it's their job to keep these VLANs logically separated and tag packets appropriately and interpret those tags appropriately and make sure that packets from one VLAN can't get to another VLAN, right? So those switches, those VLAN enforcing switches, are very security critical. Now, for hosts and edge switches that are only present on one VLAN, like for example the VLAN 102, the edge switch connecting the VPN concentrator or the public access server, SSL VPN, those edge switches may be, and the servers they're connected to don't necessarily need to be VLAN aware themselves. Instead, the backbone switch that connects them just is configured to know that, well, this edge switch or this edge host only belongs on this particular VLAN, and we don't accept tags from it. We just know that it's associated with that VLAN, and so the backbone switches enforce the policy that any packets they produce get tagged with that VLAN and can only be distributed to other, at layer 2 to other devices on that VLAN, unless they're routed via level 3 and firewall rules to other VLANs. Does it make sense? So just a general illustration how VLANs work, or how VLANs are supposed to work. And when all goes well, hopefully they usually do work this way, and they can and do provide a good compartmentalization effect. So unfortunately, they have limitations, and even well-compartmented VLAN networks have been shown to be vulnerable in various ways. Now, as I just mentioned, one potential vulnerability is just those backbone switches that are trusted to tag and untag, to attach VLAN tags and to keep all the VLANs separated. Of course, if any of those are buggy in the wrong way and a hacker can exploit that, then all bets are off in terms of this compartmentalization between VLANs. So that in principle can be a bad problem, although I'm not aware of too many major breaches that have been resulted specifically from those kind of backbone switch failures. On the other hand, there have various VLAN-based, VLAN-related attacks have been found. Other attacks that have abused or misused, in which attackers have found ways to abuse or misuse VLANs. Just to give you a few examples, one example of an issue that's actually been exploited is VLAN flooding. So to understand this fully kind of requires getting into a little bit much into the details of how Ethernet works and how switches typically learn how to route packets from one layer 2 device to another. Basically, most switches typically don't automatically know which specific device by a specific MAC address is attached to which specific switch port. Instead, they just wait until that device tries to send something, and they look at, okay, what's the source MAC address, and that way learn who's on that port or which set of devices are on that port. Now, switches can be and sometimes are configured to explicitly say, okay, this port is only for this device or this particular set of devices. That's again often the kind of the higher security can provide better security, but it takes more administrative effort. But because switches kind of by default tend to just learn where other devices are, and often don't know. This can mean that a packet comes into the switch that's destined to a MAC address that the switch doesn't know yet. The switch doesn't know which device on which port actually holds that MAC address, if any, right? And so what a switch does, any Ethernet switch in this case usually does, is it just turns it into a broadcast packet. It treats it as a broadcast packet. So I don't know who this is for, so I'll pretend it's a broadcast packet and just send it to all of the ports that are, all of the output ports on that switch that are associated with that VLAN, right? That are, potentially valid destinations for this packet given its VLAN, right? And so that ensures that, well, as long as the destination device is attached somewhere, hopefully it'll respond, and then it'll get that packet and respond, and then when the response comes to the switch, then the switch will know, that MAC address is on that particular port. Subsequent packets I'll just send directly to that port, right? So this is just standard layer 2 switch, learning, but because of this learning mechanism, this can actually be a vulnerability. So if an attacker controls a device on one of these VLANs, the attacker might be able to use one or more devices on that VLAN to flood the network, that part of the network, with a very high number of packets, say just for random destination addresses that don't exist, or actually send packets from a large number of spoofed random source addresses, like just change my device's MAC address, send a packet, change it again, send a packet, kind of pretend I'm a very large number of different devices with different random MAC addresses. And so the switch will be constantly trying to learn new MAC addresses at a high rate, and this learning will flush the old MAC addresses from its table, because these tables have limited size, and that will force other legitimate host traffic, where the next packet from legitimate hosts will miss in the table. There's some legitimate host sends a packet, and the switch says, well, I don't know who that, where that destination is, because I've forgotten it. The switch doesn't know it's forgotten it, but that's why it doesn't know, and so it treats it as a broadcast and floods it everywhere. Now, hopefully, now, if the VLAN configuration is tight, and the switch is only flooding within the ports defined for a given VLAN, then this might not immediately be a cross VLAN security issue, but it can already be a security issue, just in that the attacking host can use this flooding attack to see traffic elsewhere on the network, between other pairs of the devices that the attacker wouldn't normally see, right? So if Alice is talking to Bob, and Eve, the eavesdropper, Eve, the eavesdropper, will not, who's compromised another device on the same VLAN, will not normally see the Ethernet packets between Alice and Bob. But if Eve does this flooding attack and causes the switch to forget where Alice and Bob are, which ports Alice and Bob are on, then the next packets between Alice and Bob will become broadcast packets, and Eve will see those, right? So that's the starting point of a successful, flooding attack. It kind of gives the attacker the ability to see a lot of traffic that they might otherwise not. Unfortunately, it often gets worse because many switches are not so in the way they're configured, are often not so administratively constrained in terms of which ports are allowed to use which VLANs. In fact, switches often learn, don't have a fixed assignment of a particular port to a particular VLAN. Instead, they just learn from the first packet that comes on that port, which device, which MAC address is associated with that VLAN, and then decide, oh, based on that MAC address, I see that MAC address is associated with VLAN 3, so I'm going to, associate this port with VLAN 3, right? But then that makes this kind of VLAN or this kind of flooding attack far more powerful, because if the attacker can force the switch to forget not only which devices but which VLANs are associated with particular ports, then the attacker can see then this, the broadcast traffic the switch sends further will go, across VLANs, and the attacker can see traffic from other VLANs even, right? So this is basically a combination of bad switch design, bad administration, bad, VLANs going wrong. But it's, it's one of these things that has happened and has been created a field day for attackers. So again, just an example. There are other fun, interesting examples. So, for example, VLAN hopping is in some way even a more direct way that attackers can sometimes get traffic from one VLAN to another, and this allows them to bypass any firewall policies, routing and firewall policies that are supposed to apply to traffic crossing from one VLAN to another. So so again, like I said, many switches are the port configuration for many switches often defaults to be as automatic as possible, and sometimes this means the switch automatically tries to detect if the device attached to this port is a device, a normal end host like a laptop or desktop, or is another switch, right? So am I talking to a single device or another switch? And if a port is configured this way, dynamic auto configuration, then it's actually possible for a compromised device, like if my desktop machine is attached to one of these ports and an attacker has compromised my desktop machine, then my desktop machine can start pretending to be a switch. It can negotiate with the switch saying, hey, I'm another switch. I understand VLAN tags. I'm very happy to give you VLAN tags for the packets that I send you, and I'm happy to get VLAN tags for the packets you send me. Okay, let's all talk VLANs, right? I can do VLANs, you can do VLANs, let's talk VLANs. Which means the attacker has conveniently set himself up as if, my compromised desktop machine has basically given himself the privilege of all those backbone switches, who are, kind of the critical trusted switches that are supposed to be keeping all these compartments separate and making sure nobody can cross from one compartment to another. But, if my compromised desktop machine can make itself a backbone switch in this way, that's the networks, the entire network compartmentalization system is completely blown, right? And again, this has happened. I'm not sure how common it is, but it's one of those things. Another somewhat even more clever approach to VLAN hopping, that sometimes works when the previous attacks that I talked about were already fixed. It turns out that if you read the details of the Ethernet format, when you VLAN tag something, you insert a small, you just make packets just slightly longer, and you insert a small field just after the regular header, just to slightly increase the size of the header. And it turns out that many switches kind of don't, there's no readily obvious way to check whether a packet has a tag or not, or if a packet maybe has two tags, right? And so, so packets are never really supposed to have two tags, but some enterprising attacker realized that in certain situations it's possible to get packets with two tags through switches. So what can happen is the compromised attacker, for example, the compromised attacker is on VLAN 10, but wants to get on, wants to send an attack packet to a target on VLAN 20 in the lower right. So the attacker creates a packet with two VLAN tags, one kind of like a Tor onion routing thing, but made out of VLAN tags. And so the attacker creates a packet with two VLAN tags, one for VLAN 10 and the other for VLAN 20, sends it to the first switch. The first switch says, I see a VLAN tagged packet. Well, it's for VLAN 10. Yes, I can verify that you are indeed authorized to use VLAN 10. So, so that port is correctly configured not to allow, that untrusted machine to send packets on anything other than VLAN 10. So the switch is doing the right thing there. But the switch does not realize that there are actually two VLAN tags in the packet. So the switch strips off the first VLAN tag, leaving a second VLAN tag, which it forwards to the next switch, which says, I see a packet with VLAN tag 20, right? And then obligingly forwards that on to the target on VLAN 20, right? Now, obviously, this was not supposed to happen, right? If these switches were doing the right thing, they would the switch on the left would ensure that it either always gets VLAN tags on any port or never does, and it would ensure that that tags between the two switches in the middle are either always tagged or never tagged, and the tagging state should not depend on what kind of packet came in the input, and so it shouldn't be possible for packet data coming in from this untrusted PC above there to get interpreted as a VLAN tag. But again, it's a bug. It's switches have these kind of bugs, and they have been exploited to hop across VLANs. Yeah.
Can't we actually use like authentication mechanism or something?
Good question. Yeah. Why isn't authentication happening here? Yeah. So indeed, it seems like. So you mean like cryptographic authentication? Yeah. So that's a really good question, and it's a question that's been talked about endlessly in network both research and deployment practice circles. One of the big central problems is that, one of the problems is just legacy. There's all this equipment out there designed to understand Ethernet packets with, 2-byte VLAN tags, and doesn't know anything how to, and MAC addresses that are always the same size and non-cryptographic. They're just, they're just numbers that any device can cook up. And, actually changing Ethernet, for example, to incorporate cryptographic authentication, the expectation that when I plug in a device, it's going to exchange a key to prove who he is. That's always just been perceived as like, that would be, we would have to completely reinvent the layer 2, reinvent Ethernet, rewrite the MAC layer, create this really severe forklift upgrade of the internet. Now, personally, I think we should have done exactly that years and years and years ago. Like this is just kind of collective laziness. We've known for decades now that we should have done that, and we're totally in this heap of trouble because of our, collective laziness of not doing exactly that. But, kind of just this legacy and the desire not to make all the equipment and all the existing tools and stuff stop working until we, kind of rebuild everything from scratch. That kind of momentum is huge, right? So it's mostly that, kind of the momentum and the backward legacy compatibility thing that's kind of prevented that from taking off. And so as a result, most cryptographic security mechanisms have gone into the upper layers of the protocol stacks, things like TLS, HTTPS, where it's a little bit easier still to kind of insert new protocols, insert new things, and so so we put to the extent we do have cryptographic authentication, that tends to go in the upper layers where and it often works. It when it often does its job up there, but it doesn't really help us down in the lower layers of the network when we're talking about VLANs and network configuration. We're stuck with this kind of stuff going on. Now, I should mention that there have been major research projects to try to fix this by adding authentication, proper cryptography into the network. For example, our colleagues at ETH Zurich, led by Adrian Perig's group, have been working on, I think it's called Scion, one of the kind of proposed next generation internet architecture, kind of our network architecture redesigns that incorporates authentication, cryptographic authentication, and all kinds of good stuff. So if we could get everybody to switch over to one of the new, better design networks like that, then hopefully these kinds of things would become a thing of the past. But it's just because of momentum. It's doesn't seem like it's going to happen soon. Yeah, good question. Okay, so that's all I'll say for so that's VLANs for now. So we talked about Active Directory before, and we'll talk a little bit more about things that can go wrong with Active Directory. But let's it's probably a good time for the break. So let's take 10 minutes and come back at 5:10. Yeah, thanks.